because after the talk, 3 talks, we'll have a photo. Okay? So, just start.
Okay. Well, before I start, I really wish to thank the organizers for the invitation to come here. I realize it's been way too long that I haven't been in Taiwan. Even though this is my 4th time, but the last time is several years ago. And yes, okay, I will try to hold this. So, this is a big jump now from string theory and beautiful mathematical structures to something much more profane. In the last year, many of us were captured by this, by now elusive 750 GeV resonance that was seen in Atlas and CMS. And you know, there were 500 papers written on it, and it's kind of sad that you're not allowed to talk about it anymore. So, since a few months, I'm giving this lecture, which is trying to take a few lessons that were learned in the course of understanding this elusive particle, which I think are useful and will have some bearing also on the future. And of course, this is a very personal selection, and there's certainly many more interesting things hidden in these papers, which are interesting. I will not spend time showing you the data, because they were actually shown in the Atlas and CMS talks that we had earlier this week, but you remember that there was this nice little peak in the diphoton spectrum, which was only interesting because Atlas and CMS saw it in the same place, and because it kind of looks like the first signals we had seen from the Higgs boson in 2011, half a year before the Higgs was announced. So people took this quite seriously. The local significance was above 3 sigma in each of the experiments. The global significance, as you can see, for instance here, was below 2 sigma when you take into account the look elsewhere effect. So this triggered a tsunami of theory papers. There were even papers predicting how many papers would be written by the end of this thing. Yes, then at some point in the early summer, there were first rumors that in the new data the signal was no longer seen. And then indeed in ICHEP, we were presented the data that were also shown here, where basically with the new data, the evidence has gone away. So the question is, what is left from all this effort? I think it's fair to say that the 750 diphoton resonance would have been the most exciting new physics hint after the Higgs discovery. Also, it has triggered a spectacular overreaction of the theory community in response to this effect. I mean, certainly, you know, there were many, many papers written. Not all of them were of very high quality. I don't know what is the fraction of published papers. But it was like a swarm intelligence. I mean, if you took all the knowledge in this paper together, I think very quickly, after 2-3 months, there was a very clear picture what this new particle would be or could be, and how it would behave. And as I said, several useful lessons, I think, have been learned, and I'm going to discuss 3 of them. And the first is what I think is probably the most useful outcome of this thing at all, and it's an outcome in the context of standard model physics, namely a very precise determination or calculation of the photon distribution function. This came about because some of the very early explanations of the diphoton resonance said, well, let's do a minimal model of this particle. We know it decays to 2 photons. What if it only couples to photons? Let's just write down one interaction, just a coupling to photons. So we produce these things in photon-photon fusion, and it decays to 2 photons. And then the question was, is that enough to get the large rate that was seen? And that crucially relied on how many photons there are in the proton. And in the estimates that people did in the model building community, there were very large uncertainties in the treatment of the photon PDF. So there was this group of very clever people, Manohar Nason, Kevin Salam, and Julia Sandarigi, who thought about this problem and who found a very clever way to relate the photon PDF to the well-known deep inelastic structure function. This could have been 20 years before. This did not have to happen in 2016, but I think it happened in 2016 because there was finally a good reason to work hard on this problem. And the observation is a simple one. It's basically a statement of duality. If you look at a deep inelastic scattering process, electron-proton to electron plus x, you can describe it in terms of standard proton structure functions. So basically the electron interacts with the proton via a photon or C boson probe and probes the quark structure inside the proton. But you can also view it as a scattering of the photon field in the proton, described by the photon distribution function. So basically you can write down two equivalent formulas for this process, and in that way read off the photon distribution in terms of well-measured deep inelastic structure function. And this is this final formula that they derived. You have the photon PDF on the left-hand side as a function of x and mu square, and you have an integral over the structure functions F2 and FL, which have been very accurately measured, for instance, at Hera. And this formula is not absolutely exact. It could be made more accurate, but it's accurate enough so that it resums all the leading and next to leading large logarithms. So this is good for all practical purposes. And importantly, it contains both the inelastic and the elastic contributions. You can extract a photon from the proton and leave the proton intact, unlike with quarks. You cannot extract a quark from the proton and leave the proton intact, but a photon one can extract and leave the proton intact, and that's the elastic contribution. And how big this is compared to the inelastic one was also an important open question. So basically you plug in the known data here, you calculate this thing, and you compare to standard packages of pattern distribution. This is shown in this plot. What is shown in this plot is, so their newly determined photon distribution is normalized to 1 here. The width of the red band shows you the uncertainties in their extraction. And you can see this is highly accurate, so the errors are of order 2 to 3% for almost all values of x, and only for x above 0.8 or 0.9 they exceed the 10% accuracy range, so this is a super precise determination. And then you see in the other colored areas here, you see the existing predictions for the photon PDF, including uncertainties. And you see that the agreement is not so great. So for instance, if you take this CTEC 14 photon distribution, it's actually quite a bit lower than this very accurate determination, and it has significantly larger uncertainties, and the same is true for basically all other existing distributions. The NNPDF was in agreement with the errors, but the errors, as you can see, were much bigger than the errors are now. And this is a nice propaganda plot that I took from a talk by Julia. This is sort of the status before. This is the uncertainty there was on the up quark distribution, the strange quark distribution, and the photon distribution. You see the up quark is known within a few percent. The strange quark is known within 10%. The photon was known within 60 or 70%. And now with this new work, the photon is the most precisely known pattern distribution of all, even more precisely known than the valence quark distribution. And of course, this will have an impact on many future LHC analysis. And it will not go away, even though the reason for this study has gone away. This is a result that will stay, obviously. Now, the other two examples I want to discuss are related to new physics. In particular, new spin zero particles, because the diphoton resonance was most likely going to be a new spin zero gauge singlet, even though there were also spin 2 options that were entertained. So even though this particle at 750 has disappeared, nevertheless spin 0 gauge singlets play an important role in many extensions of the standard model. In particular, they can be mediators to hidden or dark sectors. We heard about the Higgs portal, for instance, where you couple the Higgs doublet of the standard model to a new singlet. They also play a role in solutions to the strong CP problems. They also play a role in models with axion-like particles, etc. So this is a very simple extension of the standard model that is important to understand and to study. So, if you consider a spin CO particle which is a gauge singlet under the standard model gauge group, then its only renormalizable interactions with the standard model are the Higgs portals. There's no other renormalizable couplings. And in principle, there's two Higgs portals. There is a linear Higgs portal, so S here is my new singlet. There's a linear Higgs portal coupling this to the Higgs, and there's a quadratic Higgs portal coupling this to the Higgs. And this first term is potentially problematic because this first term, if you plug in for the Higgs field, the vacuum expectation value plus the physical Higgs, then this contains a linear mixing of S with H, which means that the physical Higgs boson has an admixture of this singlet in its wave function with a mixing angle given by V over ms squared times lambda 1. Lambda 1 has dimension of mass. Naively, lambda 1 should be around the cutoff of the theory, so it's certainly at least as large as the mass of this guy. So this is not necessarily a small mixing angle. Actually, naturally, this mixing angle could be quite large. On the other hand, we know from Higgs phenomenology that possible singlet admixtures in the physical Higgs state cannot be very large. The mixing angle has to be reasonably small, otherwise all the Higgs branching fractions would be reduced by too large an amount. So it's clear that this lambda 1 has to be small. It's interesting to ask, how can you make this small? And there's two possibilities. You can make it small by means of a symmetry. For instance, you can just assume that there is a C2 symmetry and S is odd, and then this term is forbidden. You can also make it small dynamically. And I wish to discuss both options. An interesting way of dynamically suppressing the coupling lambda 1 is related to sequestering in extra dimensions, in particular warped extra dimensions. Again, we heard very nice talks about warped extra dimensions. I will show you that if you embed this singlet in the context of a 5-dimensional Rendel-Sundrum geometry, lambda 1 is automatically suppressed by a small wave function overlap or a loop factor. And then the second option, suppressing it by means of a discrete symmetry, I will consider CP to be such a symmetry. So we can imagine that the UV completion, the standard model is CP invariant. And then if S is a CP odd scalar, the coupling lambda 1 would be forbidden. So this is the two scenarios I wish to discuss. And I start with the warped extra dimension case. This is based on work I did with my former student Martin Bauer and my current student Clara Hörner. And then a few weeks later there was a paper by Javachaki and Lisa Rendel basically coming up with similar ideas and a similar model. I can skip this because Professor Hosotani gave a very nice introduction to Rendel-Sundrum models. You can read this in Wikipedia, so I guess it's common knowledge, that means. Rendel-Sundrum models were built to address the hierarchy problem, the gauge hierarchy problem, but they are also fantastic models to study the flavor problem. Because it was realized that when you move fermions into the bulk, not just gravity, one finds that fermion zero modes are localized either in the ultraviolet or in the infrared, depending on the 5-dimensional mass parameters. And moreover, that the lowest lying states, since this is an orbifold compactification, the lowest lying states, the zero modes, are chiral. The fact that the zero modes are chiral explains why the standard model is a chiral gauge theory, and the fact that they are localized allows one, if one localizes the Higgs sector in the infrared so as to address the hierarchy problem, fermions localized here have a large overlap with the Higgs and are heavy. Fermions localized in the ultraviolet have an exponentially small overlap with the Higgs, and therefore the mass hierarchies among the fermion masses is predicted to be exponentially large. And then this model also allows one to get very nice explanations of the quark mixings, for instance, in the CKM matrix. So it explains two more striking features of the standard model: chiral matter and hierarchical masses and mixing angles, along with the solution to the hierarchy problem. This is, I think, in a nutshell, why many people find these models very attractive. Now there's something peculiar about these models. When you write 5-dimensional mass terms for bulk fermions, then this 5-dimensional mass parameter has to be an odd function on the orbifold. This is simply a consequence of the fact that the scalar density psi dagger psi is odd on the orbifold. So in order to not get 0 from this integral, the mass parameter has to change sign on the two segments of the S1 mod C2 orbifold, and therefore there is a sign function here, usually written by hand. But really, this is a coordinate-dependent coupling constant now, and really such coordinate-dependent coupling constants in the Lagrangian should be derived from the depth of a field. They should not just be put by hand. So really, in order to get such a mass term, one should introduce a scalar field. Since it couples to F bar F, it has to be gauge singlet. So this is a 5-dimensional bulk scalar field. This field, in order to couple to F bar F, has to be odd on the orbifold. So this is a field that vanishes on the two planes, in the infrared and the ultraviolet. It's an odd function on the orbifold. And then the field should get a mass by means of a suitable potential here. The mass should somehow approximate something like a sign function, even though in reality it will of course have a more interesting shape. And then sort of the expansion around the wave is then a new physical degree of freedom. This is a new scalar field, 5-dimensional scalar field, coupling to fermions, and then this has a Kaluza-Klein expansion, and the lowest lying state is a new scalar particle. Because it's an odd field and it vanishes on the boundaries, it doesn't have a 0 mode. So the lowest lying degree of freedom should have mass of order the Kaluza-Klein scale, which is normally in the range of a few TeV. So basically, the statement here is that these Randall-Sundrum models with bulk matter fields, they should really always have had this field, even though in the context of warped extra dimensions, to the best of my knowledge, this was not studied before. It was studied in the context of flat extra dimensions. But in the literature, this construction is usually not part of the models that are considered. So this was a fantastic reason to have such a thing as the 750 resonance. The only thing that didn't fit is that the mass was too low, because the mass of the Kaluza-Klein excitations is usually in the few TeV range. We could lower the mass to 750 using tricks that are well known in this field. You can put terms on the boundaries to just change the boundary conditions in such a way that the masses of the lowest modes can be pulled down. This was also studied for top partners, for instance, by various people. So with some tuning, one could get a mass of 750, but now that this particle has disappeared, it's much more natural. I mean, one would really expect this particle to have a few TeV mass. But it should be there if the world is described by warped extra dimension. So why does this help to suppress this Higgs portal? Well, the Higgs lives in the infrared, and as I said, this odd field vanishes on the infrared plane, so at tree level this coupling is simply 0, and then it is induced by fermion loops in the bulk, because the fermion wave functions mediate between the bulk and the brane. So this coupling is loop suppressed, and therefore it's not of order 1, it's basically down by a loop factor. So this is a nice dynamical way of suppressing these couplings. This model has several other interesting features. The scalar, in principle, can also give rise to flavor changing neutral current couplings. But the fact that it gives the bulk masses of the fermions in the basis where the bulk masses are diagonal, the flavor changing couplings of this guy are also diagonal. So this actually has a built-in flavor protection mechanism, which is also very nice. And this model was extremely predictive. So we could just now integrating out the tower of Kaluza-Klein fermion states here, we could calculate the couplings of S to pairs of gluons or electroweak gauge bosons. And it turned out that these calculations were relatively simple, and basically at the end of the day you get expressions which essentially count the number of degrees of freedoms of bulk fermions. And the little g's here are the coupling strengths of the scalar field to the various types of fermions. But these coupling strengths are proportional to the bulk mass parameters, because that is the web of the field. And they are more or less all the same except for the right-handed top. So we could approximate all of these couplings by a universal number, G effective, except for the right-handed top, which had perhaps a different coupling. So at the end of the day, this model had three parameters, basically only two, G effective over MKK and G top over MKK. So these are the two ratios that everything depends on. And the question was, is this enough to reproduce the large diphoton signal? And the answer was, it is, even though the new physics scale here is in the TeV range. And the reason is that there's a relatively large multiplicity of heavy Kaluza-Klein fermion states. In the standard model, there's only one heavy fermion, the top. However, the Kaluza-Klein excitation of any fermion is heavy, even the left-handed up quark. So they all contribute here, and this is why we get these large multiplicities, right? So there's a factor almost 30 here, there's a factor 12 here. So this helped to lower the effective scale from several TeV to the several hundred GeV range, and therefore one could naturally explain at the time the diphoton signal. This is a plot which shows this. The blue band here is sort of reproducing the central value of the diphoton signal within 1 and 2 sigma, and these were all the bounds one had to stay away. On the right-hand sides, these were the bounds from the absence of TT bar, CC, WW signals that were not seen. And it was easy to do this, and one needed Kaluza-Klein scales. Let's say a coupling of 0.5 and a Kaluza-Klein scale of 2 TeV gave a perfect description of the data. And it would have been beautiful. We had these very predictive tables of all the various branching fractions. They could all be calculated. And then unfortunately, this thing has disappeared. But as I said, such a particle should exist in these models. It should have a mass around the TeV scale, and it has predictable interactions with all other standard model fermions. So it's interesting to keep searching for it. So let me come to the second question. What if we suppress the linear Higgs portal by means of a discrete symmetry? What if the symmetry is CP? So a CP odd pseudoscalar resonance, something like an axion. There is a natural question here. If we observe a new scalar particle, how do we know whether it's CP even or CP odd? You would say this is simple. Just repeat what we did for the Higgs boson. For the Higgs boson, one looked at Higgs decays to 2 C bosons decaying to 4 leptons. You look at the angular distributions of the 4 leptons, and there is a characteristic distribution for CP even resonance and CP odd resonance. Of course, if the resonance is a mixture, it becomes more complicated, but for a pure CP eigenstate, such as the standard model Higgs, this analysis gave very strong evidence that the standard model Higgs is CP even. However, there's a crucial difference here. The standard model Higgs has 3-level couplings to C bosons. If the new particle is a gauge singlet, it does not have 3-level couplings to C bosons, at least not at the renormalizable level. So its couplings to standard model particles are suppressed. And moreover, you can actually make this coupling even zero, the coupling of S to a pair of C bosons. So for instance, if this coupling is mediated by heavy fermions, which are SU2 singlets, then the couplings to C bosons that rate is suppressed by 4 powers of the weak mixing angle. So it's actually going to be very, very small. So the question is, can we do something different? Is there a different way to tell whether S is a CP even or CP odd particle? And we proposed this nice decay as a CP tagger. So S decaying to a C boson plus a Higgs. And then you would search. There are existing searches for this, where the C is decaying leptonically and the Higgs is decaying to BB bar. Atlas has a paper as an analysis on this final state, so this can be looked for. This is an interesting decay because this decay is only allowed if S has CP-odd couplings. So if S is a CP even state, this decay rate is strictly 0. This is very interesting because it means that ideally if you see a single event, you know that your resonance is either CP-odd, or if it is a mixed state, it has at least some CP-odd interactions. It was interesting that nobody had analyzed this decay. People had analyzed everything about the diphoton resonance except for this one decay, and I will explain to you why that was. So basically we wanted to study this process in the context of an effective theory. So we assume that S is heavy enough to decay into this final state. That means heavier than 216 GeV. I will at one point use as illustrative values 750 and 1.5 TeV, but later I will show you a plot where we just vary the mass of this state over a whole range. I should say that a very analogous discussion to the one I will present here can be done for a light pseudoscalar. If you have a light pseudoscalar lighter than 34 GeV, there is an exotic Higgs decay to C plus pseudoscalar, which is also very interesting potentially. This looks like Higgs to C plus gamma. For instance, if A decays to 2 photons, this looks like Higgs to C gamma. Higgs to C gamma is not yet measured. Currently, the rate for this process could be almost 8 times the standard model rate. This is the current bounds. So if there was an anomaly seen in Higgs to C plus gamma, this would actually be a potential explanation for such an anomaly. So this is some work in progress that we hope to publish very soon. And I should say that this part of the talk now is based on work with Martin Bauer and also a Mainz postdoc, Andrea Tam. So, remember what I told you, besides the Higgs portals, all other interactions of S with standard model particles can only come from higher dimensional operators. There are no renormalizable interactions. So of course you can now try to classify these interactions by their dimension. And the first terms appear at dimension 5 order. And they basically are obtained by taking a standard model Lagrangian and multiplying it by a power of the scalar field. And there is 2 types of interactions at dimension 5 order. There is a coupling, and I will assume that S is CP-odd now. There's a coupling of F to FF dual type expression, so I write the one for gluons here, but there's similar ones for W bosons and hypercharged bosons. And then there is a coupling to fermions, so S can be coupled to the standard model type Yukawa interactions. And here these couplings are going to be proportional to the Yukawa couplings, so basically only the coupling to the top will give rise to significant effects. So why are these 2 types of interactions? We can produce S in gluon fusion, and we can describe the decays S to gamma gamma, S to CC, S to TT bar, etc. Decays into pairs of standard model particles. Now I should give one caveat here. Even though, as I said, there were 500 papers on this particle and 500 authors used this effective Lagrangian, and we also use it, one has to be careful, because if the mass of this particle is in the TeV range, and you assume that the new physics which gives rise to these interactions is also in the TeV range, then this is a situation in which you cannot apply effective Lagrangians, because sort of you integrate out some TeV scale particles, but you keep other TeV scale particles in the game. And that really doesn't make sense unless the new physics scale is much heavier than the mass of this particle. So one has to keep this in mind. This is just a bookkeeping device. It's not guaranteed that dimension 6 or dimension 7 terms are much smaller than the leading dimension 5 terms. One has to keep this in mind. Okay, So we did an operator analysis of this decay, and I remind you again, S here is not a component in the 2x doublet model, then the situation would be very different. S is a singlet. If S is a component of a 2x doublet model, this decay actually is allowed at renormalizable level. But if S is a singlet, it is not. So, when you start to think about this, you quickly realize there's only one possible operator at dimension 5, which I can write down to describe this decay. It is an operator where I couple the Higgs current to the derivative of S. And if you work this out in unitary gauge, you get this operator, and it looks like it has everything that is required. It has an S, it has a C boson, it has a Higgs, so that should work. However,